Welcome to production theory. Production basically looks at how firms are able to convert input materials like labor and capital into output. So Q stands for output, L stands for labor, and K stands for capital. The reward for labor is rent. The reward for labor is wage, and the reward for capital is rent. So under production theory, we must understand that the lines that join points that offer the same output are called isoquants. Isoquants meet at a point where the tangency of the production equation meets the budget line. So our budget line is given by rent for capital plus wages for labor. So this is what we call the optimization problem. So we can have two inputs, labor and capital. The point at which production is optimized is called the marginal rate of technical substitution, MRTS. So MRTS is simply the point where we combine labor units and capital units to maximize our production. And using the Lagrangian function in terms of capital and labor, we use a Lagrangian function, which is given by C minus R for K minus W for labor. So this is what we call our Lagrangian function. So to maximize production, our marginal product of labor over the wage should be equal to our marginal product of capital over the rent. So this is what we call the optimum bundle. So in production, in utility, whenever we are optimizing, we need to know some calculus for us to understand how to optimize. So if you're given the production function in terms of labor and capital, so if we differentiate the output with respect to labor, call that the marginal product of labor. If we differentiate our function of quantity in terms of capital, we call this a marginal product of capital. So collectively, the point at which production is optimum is called a marginal rate of technical substitution. That point simply is when the marginal product of labor over our wage is equal to the marginal product of what? Capital over the rent. Are we together so far? With that being said, I will also take you through our minimal calculations. So if we had, for instance, our production function, which is given by 10 L to the power 3, K to the power 5. So our marginal product of labor is simply when differentiate the Q over the L. This is called the marginal product of labor. So in differentiating this, our dummy is K5. So we're going to differentiate 10 L to the power 3, which is 30 L2. So this is how we differentiate our production function with respect to labor. If we're differentiating our function of output with respect to capital, this is called the marginal product of capital. So how do you differentiate this? Our dummy is L to the power 3. So we're going to have 10K to the power 5 When we differentiate this, we're going to have what? 50 L to the power 4. 50K to the power 4. Then we leave our L as a dummy as it is. So this is what we call a partial derivative. I love to engage with my students before I start talking to myself. Let us find the derivative of this function. 100 L to the power 4, K to the power 6, K to the power 7. Who can give me the partial derivative of the marginal product of labor? How do we get the marginal product of labor? Anyone? Because for me to revise and engage you, these are the basics that you need to know. I'm of the view we are all revising. So how do you find the marginal product of labor?
Which will be, is it 400 L?
So our dummy will be K7. So we're going to differentiate what? 100 L4. What does it become? 400 what?
400 L to the power 3.
Excellent. So if we're going to differentiate to get our marginal product of capital, what becomes our dummy? Our dummy is L4. So what are we going to differentiate? We're going to differentiate 100 K7. So in differentiate 100 K7, what do we have? So our L to the power 4, we leave it as it is, and we're going to have 100 K to the power 7. So here we're going to have 700 K to the power what? K to the power.
To the power.
So this is how we differentiate this implicitly. All right. Okay, so having understood how to differentiate this partially, you must also understand that production has what we call returns to scale. So if you're looking at production and alpha plus beta is greater than 1, we call that the increasing returns to scale. If we have alpha plus beta is equal to 1, we call this constant returns to scale. Increasing returns to scale. Then if our alpha plus beta is less than 1, we call that decreasing returns to scale. So I say the lines that join points that offer the same production are called what? Isoquants. So in the illustration that we're going to have here is figure 1, figure 2, figure 3, and figure 4. So here we have 10Q, we have 20Q, we have 30Q. So we're seeing that production is increasing at a constant rate. It's just increasing at a rather scale. So this is called the constant returns to scale. But here we have the 10Q, here we have 20Q, here we have 40Q. The production here is increasing at a doubling rate. So we call this increasing returns to scale. But in the third graph, where we have 10Q, here we have 20Q, and here we have 25Q. So this is what we call decreasing returns to scale. Now, an examiner would ask you a question to explain the retains to scale on a production. So I'll repeat what I just said. Are you seeing my screen?
I'm not seeing your screen, what you are writing, sir.
Is this the same with everyone else? Are you all not seeing my screen? Hello, are you all not seeing my screen?
It's visible.
I can see.
I can
see.
Okay, so I was saying there are 3 retains to scale that you need to know.
Yeah, I
The
can
three-
see.
The 3 retains to scale simply explain the relationship that exists between inputs and outputs in production. So we're going to explain them one by one. So we have what we call increasing retains to scale. So when we are exhibiting a production that has increasing retains to scale, it means that there is an increase in the scale of production that is resulting to a proportionally larger increase in output. In other words, if we're starting with 10, goes to 20, goes to 40, goes to 8, it's doubling. So the percentage that our output, if we're going to put it here, will produce a higher output. If we're going to combine inputs of labor and capital, it implies production becomes more efficient and it expands, and this results to what we call increasing retains to scale. So you can see here, we are doubling from 20 to 10 to 20 to 40, so it's increasing. This is called increasing retains to scale, meaning we are working under an efficient production scale. There's also what we call constant retains to scale, which is a phenomenon that exists in production where the proportion of output when we fuse in all our inputs, the output that we're going to get is the same percentage. So if we're going to factor in 10%, it will increase by 10% production, same level regardless of the scale of production. Now, constant retains to scale, there is no cost advantage or disadvantage. It's like we are breaking even. Whatever we put in is whatever we are receiving, okay? So this is epitomized by graph number 1, figure 1. So 10, 20, 30, it's going and increasing at a scalar rate. Then we also have what is called decreasing retains to scale. So when you're dealing with decreasing retains to scale, basically, we're looking at a production phenomena which depicts decreasing scale, where an increase in a scale of production will result in productivity which is smaller proportional to the input we're going to put. So in other words, if all inputs are increased at a certain percentage, output will basically decrease. So this suggests that production process is less efficient and wasteful. So this is a 10 to 15 mark question that allows you to explain the retains to scale using the graphical method. Are we together on that? Are we together on that?
Yes,
Now let's go back
we're
to
together.
Yes, we are together.
So under calculus, we were saying to say that if you're dealing with output, output is denoted by what? Q is equal to our total product. When you divide the total product of labor by the labor units, we call this what? Average product of labor. When we find a change in total product of labor,
I can't see the screen.
is it the same with everyone?
Me, I can see it now.
Are you able to see
And
now?
No, I'm still not able to see the screen.
Kindly ensure
Hmm?
your internet is stable, because the screen will be lost with incoming calls or unstable internet. Okay, let me try to navigate to another screen, maybe to allow you to be able to see. Are you able to see this?
Yes, I'm able to see.
All right, okay, so now I can go back. Are you able to see this?
Yes, I'm able to see now.
All right, okay, so our quantity is the same as the total product of labor. When you divide the total product of labor by the labor units, we call that average product of labor. The change in total product over change in labor units is called the marginal product of labor. So when we multiply our marginal product of labor times the price, what we get is called our marginal revenue product. So we always make a decision to employ whenever our marginal revenue product is what? Marginal revenue product is greater than the wage. Right. So suppose we have 10 workers and each laborer produces 1,000 units. So our laborers are 10, and suppose the total product of labor for these 10 laborers is 10,000. What is the average? Average product of labor is simply total product of labor over the number of laborers. So here we have 10,000 as a total that is being produced by 10 laborers. So if we divide by 10, what we're going to get is 1,000. So the average for the 10 laborers is 1,000. Suppose an additional laborer wants to come, and this additional laborer is bringing in additional input of say 2,000. What becomes our total product for the 11 laborers? So 11 laborers are therefore going to give us what? What was there for the 10 laborers to 10,000 plus the additional that is being brought by this additional laborer, which is 2,000. What is our total product that we are going to have? 12,000. Okay. Now, what becomes our new average product for the 11 laborers? It is the total product for the 11 laborers divided by the number of laborers that are 11 now. So what is the total product for the 11 laborers? 12,000. And how many laborers do we have? We have 11. So how do we get the average product for these 11 laborers? We simply divide the 12,000 by 11. What do we get? 1090.91. Okay. Now, suppose this laborer that is joining us is asking for a wage of 25,000, and we are told that the market price is 10 kwacha per unit. So firstly, we need to calculate the worth of these 2,000 units that this man is bringing. So when we multiply the marginal product of labor times the price, what we get is called the marginal revenue product, MRP. So we're going to multiply the 10 times the 2,000. What we're going to get is what? 20,000. But this guy is asking for a salary of how much? 25,000. So if the wage is 25,000, is it worth employing? So the rule that we had initially was that you only employ if the marginal revenue product is equal to or greater than the wage. So we calculate the marginal revenue product as 20,000 compared to the wage of 25. So we discover that this person is actually eating up much of our space. So in this case, we can decide not to employ because our employee is not bringing in as much. Are we together? So we're not going to employ this particular laborer because the marginal benefit we're getting from him is not as much. Okay. So let's look at the pamphlet. I sent you some compiled questions and answers. No, just questions. Those who got okay. So we'll look at some questions on production. So let's look at some question on production to explain a few issues here and there.
Where have you sent it? It's on the group?
Yes, I've sent on the group. Okay, so under production, let's look at production. Number 4. Okay. Now question number 4 has to do with production theory, but with some calculus. So we're given in this question, we're given our production function, which is U is equal to 2 LK to the power half, and the capital is 3/4, labor is 42, and the cost is 588. So we have the cost, which is 588, and we are given our capital as 3/4, and we're given our labor as 42/4. So to start with, we're asked to come up with the optimization problem or the budget line. Who remembers the formula for the budget line? And the utility function, and the production function has been given by LK to LK to the power half. So who remembers how do we write down the budget line? The cost is equal to what? Rent for capital plus wages for what? For labor. So what is our cost? 588. Then the rent is what? 3K. And the wages are what? 42L. So this is our budget line. All together. So we can plot this. Those of you who have my videos, I think I've shared the videos for the basics. Please find time to go through them so that as we revise, you're not behind. Those of you who are really behind, make bookings during the day so that I take you step by step so that you don't feel really behind. So we explained how to plot a linear equation. So we want to find absolutely the figures that will maximize production. So to know where to cut the L, we divide 42 into 588. So to know where to cut here, and 3 into 588, we know where to cut there. So let's start with L, 588 divided by 42. You cut at what? 14. Here. Then 3 into 588, you cut at 196. Here. This is how you plot a linear equation. The second thing is to now calculate the marginal product of labor and the marginal product of capital. Ultimately, we want to calculate the point B, which is called the marginal rate of technical substitution. The marginal rate of technical substitution occurs when the marginal product of labor divided by what? The wage should be equal to the marginal product of what? Capital divided by what? By the rent. So let's differentiate this production function. So 2LK to the power half. So we distribute the halves there. We're going to have L to the power half and K to the power half. So let's differentiate our production in terms of labor, first of all. So this is called the marginal product of labor. What is our dummy in this case? K to the power half, right? Then we're going to differentiate 2L to the power half. Differentiate here, what are we getting? So when differentiate here, we're going to have half times 2 is 1. We never write 1. Half minus 1, it is what? Negative half. Then we go to differentiating with respect to capital. The marginal product of capital, our dummy in this case will be what? L to the power half. So we're going to remain with 2K to the power half. When differentiate, half times 2, it is invisible 1. Half minus 1, it is negative half. So this is going to be the derivative of what? Our marginal product of capital. Any questions so far at this point? On the derivative, anyone behind? Do I need to repeat?
You can just repeat.
Okay. So when we are doing the implicit partial derivatives, we distribute the half on both L and K. So this half comes here and this half comes there. Are we together on this step?
Yes.
Then now we differentiate implicitly. So if we're going to differentiate the Q over the L, this is called the marginal product of labor. So leave the capital alone, don't touch it. This is called our dummy. We're going to differentiate 2L to the power half. So half times 2 is 1. Half minus 1 is negative half. Are we together? Are we together?
Yes.
Then we do the same on the partial derivative for capital. So MPK. So if we're differentiating here, our dummy will be L half. So leave the L half as it is. So we differentiate 2K half. So half times 2 is invisible 1. Half minus 1, the negative is on the what? On the K. Now, if you forget this, just know if you're differentiating with respect to K, the negative is on the K. If you're differentiating with respect to L, the negative is on the L. All right. So now, who remembers the optimum bundle? It occurs at what point? MPK over what? Rent should be equal to MPL over what? The wage. So what is our MPK? LK half, but the half, if we're dealing with K, is on the on the K. Here, LK half. If we're dealing with labor, the half is around on the L with the negative. Then, what was the rent? The cost of capital was 3, the labor was 42. So K is 3, here it is 42. We're just substituting the figures there. Are we together? So now we go back to our grid.
Yes, we are.
The guy with the negative is the one that goes down. So which one goes down of the two?
it comes down.
Which one goes down?
So K over half, the negative half comes down.
Good. So K half, so here we're going to have K positive half there, right? Then here, which guy comes down?
The L negative half
So
gets
L,
down,
negative half goes down to become positive.
it becomes positive.
Correct. Then you cross multiply. 3 times 1 is 3. K half times K half is K. 1 times 42 is 42. L half times L half is L. Then we divide both sides by 3. We're going to have our final answer here as K is equal to what? 14L. K is equal to 14L. Are we together so far? Are we together where this is coming from? We divide
Yes, we
there,
are.
divide this in there. All right. So we now take this back to our original function. K is equal to 14L. So we have this function. So we found that K is equal to what? 14L. So where there is K, we're going to put what? 14L. Are we together? So we're going to substitute this. So here 588 is equal to 314L plus 42L. So here is going to be 588 is equal to 42L plus 42. So here we're going to have 588 is equal to 84L. So we're going to divide both sides by 84. So 588 divided by 84 to give us 7. So L is equal to 7. So on the L, we are now confirming that this is 7. Now, since our K is 14, so we're going to calculate K is equal to 14. This is L is equal to 14K. So what was this now? K is equal to 14L. That's what we found. K is equal to 14L. So this was 14L. So here we found L, so our L is 7. So to find K is equal to 14L, where there is a L, we're going to put what? 7. So 7 times 14, we're going to get 98. So K is 98. So 98. So how many units will maximize? We're going to find 7 units of L and 98 units of K. So this is how this question was supposed to be answered. All right, so this is how this question was supposed to be answered. So this is on production. So write down the optimization problem, how many units to maximize production, find the total output. Total output is simply, you will now substitute the 7 and the 98 in the output function. So we know output is 2L times K, the power half. Anything the power half is the square root. So 2 times 7 times 14 to the power half. So it's not 14. K is 98, L is 7. So 7 times 98. So 7 times 98.
So, Mr. Collins,
686, yes.
I was of the view that after finding L is equal to 7, we go back against the original equation we replace the 7
After finding out L is equal to 7, we have this
in
shortcut here. You will still get the same answer, but why go that far when you already
Yeah.
have A is equal to 14L? So where there's L, put the 7 there. So 14 times 7 is 98. So you
Oh,
don't
okay.
need to bother
Get
yourself
you.
as much. All right?
I get you. I get you.
But ultimately
Okay.
get the same answer. So now they'll ask you now, what is the total output? Total output, you just put it in the equation here. When you put the total output in the equation, this is 7 times 98 is 686. Anything the power half is the square root. So 686 times 2 we get 52.38 units. So these are the units that maximize production. Then we are also asked what are isoquants. What are isoquants and what are the properties of isoquants? I mentioned them. What are isoquants? What are isoquants?
Isoquants is it not same as the indifference curves?
They have the same properties, but they're different.
They're different. Okay.
Yeah?
Combinations of inputs that produce given level of output at the same rate, at the same cost.
Excellent.
Hello?
So that's correct. So I explained that. And what are isoquants? Okay, so I end my topic here on production. I have another topic here. I'll take you through. So isoquants are curves that represent different combinations of inputs that can produce the same level of output in the production process. An isoquant is also called what? An equal product curve or production indifference curve. So it connects points of input combinations that result in the same level of output. Isoquants are used to analyze production choices and determine optimal combination that will achieve a desired level of output. What are isocosts is lines that represent combinations of inputs that can be purchased given a budget or total cost. Isocosts connect all input combinations that have the same total cost. Isocosts are used to analyze cost minimization strategies and determine the most cost-effective combination of inputs given a budget. And lastly, indifference curves are curves that represent different combinations of two goods that provide the same level of satisfaction or utility. And each point of the indifference curve has a specific combination that gives the consumer an equal level of satisfaction. And indifference curves are used to analyze consumer preferences and choices as they depict different bundles of goods that are equally preferred by the consumer. So what are the properties of each? So isoquants, you discover that they all have similar properties. So isoquants have the following properties. But if you're not very good with calculations, please ensure you understand the principles of this course. So isoquants are properties as follows. They are downsloping, meaning isoquants, they stream down from the left to the right, and one input increases as the other one decreases. So they are convex, all right? So they look something like this. Okay. So they are convex to the origin. This property reflects the principle of diminishing marginal returns, where additional units of an input contributes to less and less to output as the quantity of an input increases. They don't intersect, they don't crisscross, they are parallel to each other. And this is because they represent different levels of output, and each isoquant corresponds to a specific production level. They don't overlap. The smoothness isoquants are smooth, implying that small changes in input results to small changes in output. So this suggests that there's a continuum in stem of relationship between inputs and outputs. That is regarding the isoquants. So similarly, when we go to isocosts have the following properties, and these are the properties of isocosts. Isocost number 1 have a linear shape. Isocosts are linear lines representing different levels, and they show various combinations that can be purchased at a given budget. They are downward sloping. Isocosts slope downwards from the left to the right, indicating the quantity of one input increases, the quantity of another decreases. Cost constraint isocosts represent specific budget constraints where the total cost of inputs is equal to a given budget. The combination of the inputs line is the total cost. And finally, we have what we call the indifference curves. What are indifference curves? Indifference curves have also similar properties. So here are the properties of indifference curves. Number 1, indifference curves are also downsloping, meaning they stream from the left downward to the right, representing a trade-off between two goods which represent an opportunity cost. They are convex, meaning the indifference curves are typically convex to the origin, indicating the principle of diminishing marginal utility. They are not intersecting, meaning each level has a unique satisfaction point. And finally, they have a transivity, meaning indifference curves. If one bundle of a good is preferred by another, the second one will be preferred to the third, meaning the indifference curve on top is the one that offers the highest utility than the one below it. So this is basically what I could say about production. I will rest my case.